Okay, we're going to start off today talking about phase changes, which the little review. The names of the phase changes should be a review, I guess I should say. Vaporization and condensation go between gases and liquids. Fusion and freezing go between solids and liquids. And gases and solids, you would use the terms sublimation and deposition. As you move between these three, you will see that the enthalpy of the system increases as you go from solids to liquids and then to gases. And remember that the symbol H represents the internal energy, aka the enthalpy of the system. And so we actually only have two symbols that we will use for the enthalpy of a phase change, and they are delta H of vaporization and delta H of fusion. And from there, we will really just use a few alterations, I guess you could say. If you take and look even at the picture, the opposite of fusion is freezing. So if you know that, for example, the delta H of fusion is 5 kilojoules per mole for a substance, then the delta H of freezing should be negative 5 kilojoules per mole. So we know that the delta H of freezing is the negative of the delta H of fusion. So that would mean that the delta H of condensation is the negative delta H of vaporization. I know I'm not doing a very good job writing sideways, but I'm paranoid I'm going to hit the stop sign on the video recorder like I did last time. All right, and then sublimation is actually the addition of the delta H of fusion plus the delta H of vaporization, both of them added together. So deposition is the negative of the delta H of fusion plus the delta H of vaporization added together. So really, you only need to know the delta H of vaporization and the delta H of fusion, and you could know all 6 of these values. All right, next on the agenda, the enthalpy of the phase change formula. So far, you've learned the formula Q equals mc delta T, which is the formula for a temperature change. But if you recall from our online lab, when you were dealing with adding heat to a substance, you didn't always see the temperature change increase. Sometimes it would flatline, or what we call plateau, or hit a plateau. And that's because at certain points it would involve a phase change. It would hit its melting point or its boiling point. And once then it would be done with its boiling or melting or whatever it was doing, then it would continue on to heat up or whatever. And so if you don't have a temperature change, you can't have a delta T. So you couldn't use that equation, Q equals mc delta T. So you got to have another formula, and we have our Q equals what's called N delta H. So what is happening during a phase change if you're not using the energy to increase the speed of the particles and increase the temperature? What you're doing is overcoming the intermolecular forces. So that's what's happening during a phase change. That energy is still being input into the system, but it's being used to overcome the intermolecular forces. So our equation could be Q equals N delta H, or sometimes I need to add this, Q equals M delta H. Sometimes they'll let you use M, which is mass. It depends on what your delta H is. If delta H is kilojoules per mole, you're going to use N equals moles. If delta H is kilojoules per gram, then you get to use your M as grams, meaning mass in grams. All right, so Q is still heat energy in joules or calories, or I should say, or kilojoules. N is moles. Delta H is the molar heat of a phase change specific to whatever phase change you're studying. So if it's vaporization, fusion, whatever you're looking for. And you just need to figure out which one you're studying. So we're going to do a sample problem here. Calculate Q when 1.50 grams of water freeze. So the first thing you need to look at is what phase change that is. Freezing is the opposite of fusion. So fusion, delta H of fusion is 6.02 kilojoules per mole. So keep that in mind. Q equals N delta H. We also know this is 1.50 grams of water and 1 mole of water. If you remember, weighs 18.02 grams. So I'm going to take 1.50 divided by 18.02 with 3 sig figs. That's 0.0. Remember, 0 is not a sig fig. 1.50 divided by 18.02. 0.0832 moles of water. So Q equals, and this was for freezing specifically, but we know that's equal to N times the negative delta H of fusion, because freezing is the opposite of fusion. So let's plug in chug now. N, we said, is 0.0832 moles, and fusion, negative 6.02 kilojoules per mole. Moles cancel. We're going to take our 0.0832 times 6.02 negative equals, and we get negative 0.501 kilojoules. Problem is they want this in joules, so now we're going to convert that. We know 1 kilojoule is 1,000 joules, and so this becomes 501 kilojoules is your final answer. All right, next on the agenda, heating and cooling curves, which is very misleading because, just like I mentioned earlier about our lab, when we plotted our temperature over as time went on, it wasn't very curvy. It was a bunch of jagged lines. And so these are called curves, but they're really just a bunch of jagged lines. When we set them up, understand you're going to have a maximum only of 5 regions. Why? Well, because we can only have a max of 2 phase changes and 3 temperature changes. That's the maximum you can have in a heating cooling curve. So how many will your problem have? Well, you got to look at your overall temperature change versus your melting and boiling points and see, do you exceed both? For example, water boils at 100 degrees Celsius and melts at 0 degrees Celsius. So are your temperatures, are you starting off at -5 degrees Celsius and going to 105? If that's the case, you're running the whole gamut, and you're going to have 5 regions because you're going from below your melting point and going above your boiling point. However, if you're starting at 25 degrees Celsius, you're already at a liquid, and you are going to be not where you're going to be at a solid at all. So you wouldn't have a max of 5 regions. So you just have to look at whatever situation you have. The second thing you need to look at is, are you going to be dealing with a heating or a cooling curve? And that's just common sense. Like, what temperature are you starting off at? What temperature are you ending up at? If it's a heating curve, you're starting off low, and if you're a cooling curve, you're starting off high. Understand you're sketching these curves. It is not quantitative. So please keep that in mind. You do not have to have a set, you're not plotting points. You're not plotting points, so don't think that you have to have specific dots and certain points. Your axes, I know I put reaction in here, but you can get rid of that. Your x-axis is going to be time, or just the progress of whatever's happening, and your y-axis is going to be temperature. But again, not specifics. You are going to want to put your temperatures in there for your melting and boiling points. So melting points, boiling points, and your beginning and end points, but those are the only temperatures you should have in there. So you should have 4 temperatures in there. And we're going to do we're going to be doing a sample problem, so that shouldn't be hard there. All right, so next we have temperature change. So as I mentioned, you're going to have a couple temperature changes in here, or could have some temperature changes in here. Note that when you do a temperature change, that's when you're going to be using that equation we learned the other day, Q equals mc delta T. During a period of temperature change, energy added or removed is affecting the motion of the particles. The line in this portion will have a slope. The unit in this, because C is in units of joules, understand your Q will be in units of joules. During the phase change, we just learned that your equation will be Q equals N delta H, and your unit will be in kilojoules. This is important because when we add these together, you're going to be adding your 2 Q's together, and so you'll have to make sure that you get your units to jive here. During a phase change, the energy added or removed is not affecting the motion. It's being used to create or break intermolecular forces, so no temperature changes noted. Because of that, your line will not have a slope, so instead it will have what we call a plateau. And this is a heating or cooling curve example. So here we have a temperature change. Here we have a phase change. Here we have another temperature change. Here we have a phase change. And here we have a temperature change. So this is an example that we're going to do in my next video. And you will add up all of these to get your final answer.